No, but I suppose, yeah, I was just, yeah, so it'll just stop here. Okay, so yesterday I showed you that the response function of any system, particularly quantum systems, can be written in this form, where n are the exact eigenstates of the Hamiltonian, and this plus sign, the minus sign will come here if these operators are, I will use the word bosonic, there will be quadratic and fermion operators, for example, and if they are like, if this were like the retarded Green's function of the particle, for example, these would be single fermion operators, and that's why I just call it fermion. Okay. So today what I will do is I will play. We'll start with a little game. Okay. We will do some things which look somewhat strange. So we'll just play with imaginary time. Okay, the game is real, only the time is imaginary. Okay, so the idea is the following. You look at the density matrix associated with the thermal distribution, you will see that that is sort of related to this operator. Okay, now suppose I just were to put a little bit of space here, right, and stare really hard at this point, you will see that a minus I square will appear. You see that? Minus I square is 1, right? Okay. So what you do is you rewrite this object as e to the minus I minus I beta h. Okay? So suddenly you realize that the thermal distribution is as if there was a propagation in imaginary time. So remember that e to the minus ith is the propagator, is the Schrodinger evolution operator, right? And you see that this operator actually is Schrodinger evolution operator in imaginary time. That's what it is. Okay? All right. So we are now sort of motivated to see what happens in imaginary time. So what I'm going to do is I'm simply going to take tau and call it imaginary time. Right? And I'm simply going to define an operator which I will call as us of tau, some Schrodinger evolution in imaginary time, and this would be just defined like this. Right? This is simply a definition of this object. Okay. So if I were to write out some equation for equation of motion of this, you will see that this will satisfy this very nice equation which you can easily write down. Something like this. So this is the equivalent of the Schrodinger equation in imaginary time. That's what this is. Okay. All right. So now what we can do is we can actually define Heisenberg operators in imaginary time. Right? So for example, I could define something like this. A tau, this is equal to e to the tau h, like this, a e to the minus tau h. Right? I'm simply defining this. Okay. Now, a tau can be either a bosonic, this quadratic and fermion operator, or just a single particle-like operator. It can be any one of these things. Okay. All right. Now, what I'm going to do is I'm going to define something which I will simply call as chi ab of tau. I'm just calling this as chi ab of tau, and this by definition is equal to this. That's by definition. Okay. So I have not told you what this t tau is. Okay. So now let me define t tau. T tau is called as the imaginary time ordering operator. It's not like an operator in Hilbert space. It's called that, right? It's the time ordering rule, if you like. Right? And what is the rule? The rule is the following. T tau of A tau B tau prime is equal to A tau B tau prime if this is if tau is greater than tau prime. So if this is a later time than tau prime, then this is what it is, and plus minus B tau prime A tau if tau prime is less than tau. Okay, this is the definition of this object. Sorry? Tau is real to start with, yeah. Tau is real. Sorry? Oh, yeah, tau is less than tau. Okay, I will write it like this. Okay, so that is the definition. Now what is this plus? This plus is for the bosonic stuff. So the plus is for bosonic operators, and this minus is for fermionic. Okay, so this is the definition of this object. Okay, so now you can ask, what will you do with this, right? So in this definition, this is tau prime. In this definition, tau and tau prime are allowed to here. Tau and tau prime are allowed to be between 0 and beta. That's what we will say. So is tau prime. Now what I can do is since this object actually depends only on tau minus tau prime, you can actually show that explicitly. You can define a new tau which goes from minus beta to plus beta, and you can simply define it like this. Right? So you can define it like this, and here tau would be in this, would be here, something like this. Okay, good. So why would you do something like this, and what can you get out of this kind of stuff? Okay, so let's see what we can get out of this kind of stuff. So first thing is, I want to show you some properties of this guy. Okay, so let's say that tau is greater than 0, and I ask what is chi AB of tau minus beta. That's what I'm asking. I'm asking a question. What is this quantity? Okay, so can you tell me what it is like? What is this quantity? So this turns out to be equal to plus minus chi AB of tau. Okay, can you see that? Okay, so let me just show you that. So if I do this, since tau is greater than 0, tau minus beta is negative. So when I do the time ordering, this term has to come next and the B has to come first. So this quantity is equal to chi AB plus minus, right? Because I pick up a minus sign, because for this guy I will pick up a minus sign. And then what do I get? I get, plus minus, okay, sorry. So this will be minus plus T tau B0 A of tau minus beta. Right? Minus plus because there is already a minus sign, and I flip this, this will continue to have the plus sign. Sorry, mistake. Yeah. So I have this plus minus, so then once I do the time ordering, I have minus plus tau. Thank you. Okay. All right. So now we can use the definition of what that is. That is trace of e to the minus beta h, right? B of 0 is simply B, and this is e to the tau minus beta a e to the minus tau minus beta, like this, right? And what I will do now is, I will use the cyclic invariance of the trace, right? And I will move these operators around, and I can rearrange things in such a way that this thing comes back to whatever I have written here. So that's how this is proved. Okay? So if you have not seen that in full detail, you should work this out yourself. So the idea here is to use cyclic invariance of the trace. Okay, and then you will see that this result holds. Okay, very nice. So now what do I have? I have a function which is defined on this interval minus beta to beta, right? So anytime I have a function defined on some interval like this, I can write some Fourier representation of that, right? So if I have some function f of tau defined on minus beta to beta, I can always write a Fourier representation for this. Okay, so let me just do that. So I will simply write this as e to the I some L, let me say, or let me call it, what should I call it? L, let me say, e to the minus I omega L tau f of I omega L. So what is omega L? What is omega L? No. So I have written sum over L, e to the I omega L. I am doing Fourier expansion. So what is this omega L? Omega L will be 2 pi L integer divided by the length of the interval, which is 2 beta. Right? This is omega L. So this is generically true. Okay? Everybody is okay with this? Yeah? Okay. All right. So now let's use this formula with our response function here that we have written in imaginary time. So I will have chi ab of tau is equal to, I may change the notation a little bit later, but let's just do it this way. Okay, this is what I have. Now, if these are both bosonic operators, then what will I find? I will find that if I substitute for this beta minus tau minus beta, I would get e to the minus I omega L tau minus beta here, right? And then this would be again chi ab of I omega L, and this should be plus or minus chi ab of tau. That's what my statement is. So if that has to happen for every tau positive, then that tells me something about this guy. What does that tell you? Because you can see that this quantity I can factor out to the I can just take the e to the minus I omega L beta multiplied by e to the minus I omega L tau, and since these two are equal for all taus positive, that means for the bosonic case this must be positive for bosons, right? This is plus 1 for bosons and minus 1 for fermionic operators, right? So this should be plus 1 for bosonic operators and minus 1 for fermionic operators. Then that identity will be identically satisfied. Okay? So what that will mean is for bosonic operators, so let me just put that here. This means that e to the I omega L beta must be equal to 1, and for fermions, for all L, it must be equal to 1, and this must be equal to 1 minus 1 for all L. So immediately you see that the L's that are allowed in this case are only even numbers, right? And the L's that are allowed for the fermionic operators are only odd numbers. Okay? So what we will call is, these are even frequencies. So we will give them a name. We will call them IQL. We will call Q as the even numbers. And these guys we will call as IKL. So KL will always stand for odd frequencies and QL will stand for even frequencies. Okay? These are also sometimes called as Bose and Fermi Matsubara frequencies, after Matsubara, of course. Okay, so this is the statement. Okay, so here's I will slightly modify that definition, but that's a trivial modification. So what I will say is that for bosonic operators, this is defined. There's a convention to put a beta 1 by beta here. Sum over IQL e to the minus IQL tau chi ab IQL, and for the this is for bosonic. And for the fermionic operators, this would be 1 by beta some ikl, and this is e to the minus ikl tau chi ab of ikl. Okay? Sorry, there is a question? Yeah. Okay, so this is the game. Okay. So far I haven't done anything actually. I've just played with some some mathematics and derived some Fourier transforms and so on. That's all I've done. I've not done anything fancy. Thank you for asking that question. The answer to that question will become clear. Yeah. So you can see that there's something written on the top left-hand corner. Okay. Okay. So now what I would like to do is I would like to find what is this quantity. I would like to find out what is this quantity chi ab of IQL or IKL, depending on whatever my problem at hand, whether it's fermionic or bosonic operators. I would like to find out what that object is. And in terms of what, I would like to find that object in terms of the exact eigenstates of the Hamiltonian. Okay, that's what I want to do. So in other words, I want to find a Lemon representation for this guy. And so here's the magic. Okay, so if you work this out, which I urge you to do, you will find that this quantity is equal to some mn Pn minus plus Pm NAM MBN divided by IQL or IKL, depending on which one you are looking at, minus omega mn. That's what you will find. Right? So you are supposed to say right? Why is that? Because you see, what we had started off with is that we said that there is something called the retarded correlation function or Green's function or response function, which we had written that, I'll just remind you, chi ab of t minus t prime, that is equal to minus I theta of t minus t prime at bt prime. This is what we had actually derived, and this is a real physical quantity which you can measure and so on. Right? That's what we have said. Okay. Now what did I do? I played some game. I just defined some object, some imaginary time, something that we don't understand on a day-to-day basis, at least. So if you have not realized, for example, this operator which I wrote down, e to the minus I tau h, that's not even unitary. Right? So it should all be very strange to you. Right? If it is not, well, it's good. Okay. All right. So this object you have, if I go to the Fourier domain on the real frequency line, it looks like omega plus. So then the Fourier transform of this guy, Fourier transform, looks like chi ab of omega plus. That's what we showed. Okay. Now I played some game and I found some object which is defined only at Matsubara frequencies. Right? So let's just recall what that means. So if I have bosons, if I have bosonic operators, I have this object, these guys, defined only at Matsubara frequencies. So this would be for the bosons, right? All the even frequencies, right? And for fermions, this is for bosons. And for fermions, you would of course not have the 0. You would have all the odd frequencies. Let me put them by dots, right? So there will be 1, 3, and so on. Right? So what you are seeing is something quite remarkable, is that this piece of this stuff which is defined for imaginary time, its Fourier transform, which is defined only at discrete Matsubara frequencies, that object is same, quote unquote, as what you would have gotten if you had taken this formula and stuck in IQL here or omega plus. Right? So what we have defined in this, whatever game we played, it has some serious consequence. So if you are able to calculate this guy, you will be able to pull off the values at these Matsubara frequencies. And if you know the values at those Matsubara frequencies, then it is possible for you to reconstruct that function everywhere in the analytic plane, everywhere in the complex Z plane. Okay? So that's actually the game. So the game is you will find some techniques to calculate this on these points, and then what you would do is you would analytically continue this. So this arrow is, by that we mean analytic continuation. That means if I know some function which at some possibly infinite set of points, maybe discrete points, I try to find out what is that function everywhere else. Okay, and I know that this function has to be analytic in the upper half plane. It is allowed to have any kind of difficulty or poles or whatever in the lower half plane only. So using these two pieces of information, I can try to reconstruct that function, and from there I can try to calculate this quantity, which is the real physical response. Okay, so now you may wonder, why would somebody do this, right? So the reason why why this is natural thing to do is, in one fell swoop, you will be able to solve the problem at any temperature, for example, because this formulation will work at any temperature, right? And then it also turns out that you can use some nice field theoretic techniques to do these calculations. Okay, to actually extract some of these things. You'll be able to find some nice techniques to calculate these guys, for example. So if you do Quantum Monte Carlo, so if you want to calculate the Green's function, if you read Antoine's paper which I showed you yesterday, there is actually an appendix there which shows you how to calculate the Green's function as a function of tau using Quantum Monte Carlo. Okay, so you would actually get this g of tau, and then from there you would go to this IQL. You will get that piece, that piece of information, and from there you will try to calculate what is the spectral function, for example, by finding what is g of omega plus. Okay, that last step is easier said than done, and that is actually a problem. It's called analytical continuation problem. Okay, and I'm sure that as we in the school that will be discussed at some point at least. Okay, so this is the connection, and this is why we want to go to imaginary time. And if we go to imaginary time, we can do all these calculations in some nice by using some nice techniques, and from there get the response at real frequencies by analytical continuation. So this is the game. Okay, so any questions at this point? Okay, great, wonderful. I should pat myself on the back. I won't do it because I'm actually may sprain my hand. Okay, so let me proceed then. And what I will now do is I'm going to develop some more understanding of what these imaginary time things are.
Which is countably infinite, sorry, uncountable, but now you are going from uncountable to countably infinite. I mean, so yeah, I said it's not well defined, but it seems
it's a very well defined question. It's very well defined question.
Yeah.
So that's where complex analysis comes to play, right? So if you have some analytic function, there's very little freedom you have. So for example, there's the famous Cauchy's theorem, right? That if you know the analytical function on some line, you can actually find it anywhere else.
Yeah.
Right? So now the question you're asking is, if you reverse that question instead, you can ask the following question, that if I know the values of the function at all the Matsubara points, is the function uniquely defined everywhere? Okay, that's some difficult question, and there is some Watson lemma and some big famous mathematicians of 18th century have worked on that. Okay, whenever I need to use it, I'll go and find out.
Okay.
That's the answer. Okay, other questions? Okay, if there are no other questions, what I'm going to do is I'm going to take a particular example of this chi AB of tau, and I'm going to look at its properties, and you will realize very soon that whatever I'm going to discuss has a lot to do with, for example, the formulation of DMFT and so on. Okay, so let me just define this object, which I will call as GAB of tau. A and B are any suitably chosen one particle states. Okay, so this is called as the temporal Green's function or finite temperature Green's function. It's called variously. Okay, so this is the object, and in our case, if you want to make a connection to this, this is a these two are fermionic operators, so we should use all the formulas all the fermionic formulas. That's what we should be doing. Okay, that's the idea. Okay, so that's the definition of this object. So let's try to calculate this object for free particles. For free particles, let's try to understand what this object is. Okay, so for free particles, the Hamiltonian you know very well by now. So this is sum over all momentum states. I have defined this already. Okay, so this is the Hamiltonian. Okay, so what I would like to do is I would like to calculate this Green's function, and the natural set of states to look at the AB states here are these, the momentum and spin labels, right? Those are the the natural one particle states. So I would like to look at I'd like to look at this quantity. So I want to find out what this quantity is for this for the free fermion. So this is minus, again I will just write all these things down. That's what that quantity is. Okay, we can even just put tau prime there. Okay, good. So can you tell me what that quantity is? Can you tell me how you would go about calculating this? Okay, so the trick is the usual trick. You find out what is this quantity. So what is that quantity? So this quantity, yesterday somebody had given the correct answer, right? Somebody had given the correct answer for this yesterday. So it will be the same thing actually. So this will be actually minus tau Ck and then Ck sigma like this. That's what it will be. Okay, good. And there is a similar formula for C dagger K sigma of tau. And if you naively do complex or the conjugation of that, you will get a wrong answer. Right? Because this is real. And if you complex conjugate, nothing will happen. Right? You will get a wrong answer. So that's what I was telling you about this being not unitary. Okay? So this quantity is actually e to the tau Ck and then Ck sigma. Okay, so those are the two results we need. And once we have these two results, we will be able to derive what this formula is. And let me tell you why I'm doing all this. What I want to do is, I want to find a differential equation. I want to find a differential equation that will be satisfied by this object. That's where I'm heading towards. Okay, that's why I want to do this. Okay, very good. Why do I want to find the equation of motion for this? Because yesterday I showed you something written down by Antoine, because one of the terms in that will be this. That's already been motivated. Okay, all right. Okay, so here's the stuff, and I just stick it in here. It's very easy, right? So let me just do this. So this quantity, which I will just abbreviate as G, this quantity is minus theta of tau minus tau prime. I'm looking at the positive values of that, and that will be, I pick up these two factors, Ck here, and then e to the tau prime Ck prime multiplied by expectation value of these operators now. So that will be Ck sigma C dagger K prime sigma prime. Okay, that's for the positive values of tau minus tau prime. For negative values of tau minus tau prime, I must write a separate term with an appropriate theta function. Right? So what do I need to do? I need to put a plus sign, because they are fermionic. When I flip them, I will get a minus sign which cancels that minus sign. Then I'll have theta of minus tau prime, theta of minus tau prime, right? And then there will be the same factors, e to the minus tau Ck and e to the tau prime Ck prime multiplied by expectation value of C dagger K prime sigma prime Ck sigma. Good? Everybody's okay? All right. What is the expectation value of Ck sigma C dagger K prime sigma prime? Who is saying that?
Yeah. Delta function multiplied by some distribution function.
Correct, that's correct. That's absolutely correct. Thank you. So this quantity is actually 1 minus NF of Ck multiplied by delta of K prime, delta of sigma sigma prime. That's what that quantity is. This guy. And this guy is delta K prime, delta sigma sigma prime, NF of Ck. That's what that quantity is. Now what is NF? NF is the usual Fermi function. NF of x is equal to 1 by e to the beta x plus 1. That's what Fermi function is. Okay, so this is what you get. Okay, now that looks a bit grotesque, but it's not so bad, and you will see that it actually simplifies very nicely. Okay, so I hope I don't have to rewrite that. I want to do some manipulations with that. Okay, all right. Okay, let me just rewrite it anyway. So this is K sigma K prime sigma prime of t minus t prime, and what will I have? I'll have minus theta of tau minus tau prime, and here I have this delta function. I have these delta function K prime and sigma sigma prime. So these guys will get, the K will become, one of the K primes will become K. And what will I get? I'll get e to the minus tau prime Ck I will get here like this, and then I will have 1 minus NF of Ck plus theta of minus tau prime, and the same factor will be there, the same factor will be there, multiplied by NF of Ck, the whole thing multiplied by the delta functions. This is what I will have. Okay, that's the final answer. Okay, any questions? No, I use the delta function. Therefore, I am able to write this as e to the minus tau prime psi k. But then I have these two labels on the left hand side. So I need to hold on to those guys. So I can drop all the delta functions and simply call this a diagonal object, which is fine. If I don't, then I need to hold on to those objects. Let me hold on to those objects, because there is a reason why I want to do that. Okay, good. This is all algebra, nothing fancy. Okay. Okay, now what I would like to do is I would like to look at what is d by d tau of this quantity. I would like to see what that is. Okay? Okay, can you tell me what that is? Actually, there will be two terms, right? This is actually a product of two terms. It's a product of a theta function multiplied by some function. Okay? So as long as you are not at the point where tau is equal to tau prime, then you don't need to worry about the theta function. Okay? You need to worry about the theta function only when tau is equal to tau prime. Right? So let me just do the calculation. So what will I do? If I just get, if I take a derivative with respect to them, I will get a delta function, because derivative of a theta function is a delta function. So what will I get? I will just get delta of tau minus tau prime. And at that point, when this fires, this quantity is 1. So I don't need to worry about this quantity. So that will be 1 minus NF of Ck. That's the first term. Now I am taking the derivative with respect to the second term, and what that will give me is, that will give me a minus sign, because there is a minus sign here, and that will again give me the same delta function. You may wonder that, oh, why should I have the minus sign, but delta function is even, so I don't need to worry about that. So this will be delta function of tau minus tau prime, and this will be again nf of ck. Okay, and then I need to take the derivative with respect to this tau in the other term for any other value of tau. Okay, and you can see immediately that that will be just ck minus ck, because I'll just pull down this guy, and it will be the same thing remaining, g k sigma k prime sigma prime tau minus tau prime. That's good. Okay, now let's simplify this guy, right? When I simplify that guy, what happens? You see that this will become a plus nf of ck, this is minus nf of ck, so it cancels. So I can dog this guy off, I can dog that guy off. Okay, and immediately I find that this fellow satisfies this very nice equation. Okay, it satisfies this equation. So this is the differential equation satisfied by the Green's function. Right? Are you surprised? Sorry? Oh, okay. All right. So actually that's just the Schrodinger equation actually, if you think about this. Okay. Any questions? No questions. Okay. Now what I want to do is I want to play a little game again. So you see, okay, there's a mistake here. Can you see what the mistake is? So there should be a delta k k prime, delta sigma sigma prime. Okay. Now what I would like to do is I want to reinterpret this Green's function in a slightly, if you like, with a mathematical flavor. Okay. So you view this Green's function as a matrix. What are the elements of the matrix? So there is a row of the matrix and a column of the matrix, right? These set of objects, k, sigma and tau, you view as the row of the matrix. And k prime, sigma prime, tau prime, you view as the column index. So this is now some infinite dimensional array of numbers. You can visualize that, right? So one of these arrays are, one of these indices are continuous, but okay, we have seen worse things in life, right? So we are not worried about that. Okay, so that's what this is. So what I want to do now is, I want to ask, what is the inverse of that matrix? So this is the Green's function matrix, if you like. What is the inverse of that matrix? Yeah, that's my question. Okay, so I will show you what the inverse of that matrix is. Okay, what is on the right hand side? Can you tell me what is on the right hand side? I said that that's a matrix, right? This is the identity of that space of matrices. The right hand side is the identity of in that space of matrices, right? That's what that is. Okay, so what you do is you just look at this quantity d by d tau, my plus open bracket plus ck, and leave out some gap here. Okay, and then let me just write and put this k prime sigma prime and minus tau prime is equal to delta of tau minus tau prime delta k k prime delta sigma sigma prime. Okay, now I want to fill those gaps. Okay, so what I'm going to do is I'm going to sum over k1 sigma 1 and integrate from 0 to beta d tau 1. Okay, and what I'm going to do is I'm going to multiply here by delta of tau minus tau 1, and I'm going to write a delta k, what do I want, k k1, and okay, I'm just running a little out of space. So let me just squeeze that in, delta of tau minus tau 1, delta of k, k1, and delta of sigma, sigma 1. And here I am going to write k1, sigma 1. So what I have simply done is, this k sigma and tau I have simply rewritten in terms of some delta functions, right? But then suddenly you realize that if I call this object, as G inverse, right, K sigma, these labels, yeah, thank you, yeah, okay, and then there is just a tau 1 here, so I'm done, yeah, okay, tau minus tau 1, and then this will be G K1 sigma 1, okay, this is K1 sigma 1, K prime sigma prime, tau 1 minus tau 1 prime is equal to delta function tau minus tau prime, delta K K prime, delta sigma sigma prime. Good? Yeah, question?
This equation of motion for Green's function.
If you see it as what equation?
This differential equation. If you see it as a matrix equation,
yeah,
means it's not quite clear to me how you define only left inverse.
Of course, you can define right inverse as well, but left inverse is good for me. So I mean, for my purposes, that this will suffice. So you can do many things, right? But we are just doing what we need. You're absolutely right. Yeah. Okay. So in this case, actually, the right and left inverses and all will be same. So you don't need to worry. Okay. All right. So this is the relation, and now you see this very nice result, which is actually which will be our workhorse in some sense, right? So you can see that this is like, I'm multiplying two matrices. So this is the column of the first matrix multiplying the row of the other matrix, right? One of the indices is continuous, but that's okay, right? And that's the tau 1 index, which is continuous, and you have a nice definition of the inverse. So what is the definition of the inverse? Definition of inverse, K sigma, K prime sigma prime, I'm going to call it like this, tau minus tau prime. The inverse is equal to this quantity, minus d by d tau plus Ck, delta of tau minus tau prime, delta K, K prime, delta sigma, sigma prime, right? But this is actually, this is nothing fancy here. So for example, if I want to write the Green's function, I would write the Green's function as the inverse of this object, right? So I'm writing that in the opposite way, that's all. Okay? Okay. Any questions up until now? Any questions? Okay? No questions. Okay, good. All right. So what I'm now going to do is, I'm going to ask, what happens to this quantity if it were not free fermions? So for example, if I had this piece in it, this U piece, right? This piece is already included because that's C, right? If I had the interaction piece, what would happen to this G? For example, will the G inverse be exactly same as this, or will it be something else? That's the question I'm asking.
I think it will have some non-diagonal, off-diagonal.
Why do you want it to have off-diagonal terms?
It may give rise to some off-diagonal.
Why are you saying that? So, I mean, what is the reason for saying that it? See, if you say it may happen, it's always true. So you've covered your bases, right? So, but why are you saying that? Actually, it's not true at all. Actually, unless you break some symmetry, it will not give any off-diagonal terms.
At the first place itself, if you have interaction, you wouldn't have written those equations.
No, I would not have written those equations. And
no, yeah, that one.
Yeah. So what you are suggesting is, based on whatever I have done, there is no reason to believe that G inverse when I have interactions will look like this. We are agreed. So what else will we get? That's my question.
Maybe some other complex object.
That is an even more correct statement than what he made. Now you're okay. So I see. So okay. Fourier transform something.
No, we use
Okay. No, you made a comment, right? He made some comment. Let me just finish the discussion with him. Yeah. So what is your point?
So I think going by that G inverse equation, you will have the Fourier components of the interaction in front of the delta function. That will be the operator.
Okay, very nice. I think you're having some correct physical idea there. Okay. So suppose I were to put an additional potential in this, not an interaction. I put a potential.
Okay.
So for example, I suppose I were to put in this is no longer free form. And suppose I were to put in something like V k prime, some scattering between some states, k sigma and c k prime sigma, like this. So I take some stuff and then what would happen?
You will put V k prime
Okay.
over there.
Roughly correct. It's not exactly going to be VK prime, but it's roughly correct. And then actually you will get non-diagonal terms, right? You get non-diagonal terms because this Hamiltonian does not conserve momentum, right? So if I put in a particle at momentum k, I may be able to pull it out at momentum k prime because the potential will take my particle I've put and scatter it somewhere else. If I didn't break any symmetry, there is no reason to get any off-diagonal terms. Okay. So what you are saying, if I have a static potential like this, which is not time dependent or anything, you're right. I will get something that looks like VKK prime, then I have to rewrite these equations in a more careful way.
Yes.
Exercise. Please do it. Right? It's a very good exercise for you to write out what is the Green's function if I have that scattering potential. Okay, and it's also important for DMFT and all that. Okay, so that's what will happen. But you see, I have a system in which this potential is not a static potential. It is the interaction between the particles,
Yes.
which is dynamic generically. What do you mean by dynamic? Okay, so what I mean by dynamic is the following. Suppose I had a particle here. The effective potential it will feel will depend on instantaneous picture of what other particles are doing.
Yes.
Right? And the other particles are not going to hang around. They are going to move around because it's quantum mechanics, right? So they'll be fluctuating around.
Yes.
Right? So what this particle will actually see is some retarded potential, some kind of time dependent potential which is causal. What that means is, if some other particle moves here, after some time or at a later time, this particle will feel that it has moved. So it will see a time dependent potential. That's what it will see. Okay? So I'm skipping a lot of the syllabus and I'm telling you the final answer, what it's going to look like. Okay? So what I will end up getting if I have interacting system is that the G inverse will look somewhat different. Okay? So there the G inverse of k sigma k prime sigma prime of tau minus tau prime will have exactly the same piece that we had without interactions, in the absence of interactions. That is this same object that will always be there, of course, right? So this will have minus d by d tau plus ck. What else? Okay, delta of tau minus tau prime, delta k k prime, delta sigma sigma prime, the usual stuff, plus. And for conventional reasons, I will write minus here. I will introduce a quantity called, what that is I have not calculated, but I'm perfectly allowed to write this. Right? This is the self energy. Okay. If you read high energy physics literature, this is called as the mass operator. Okay, both they're all actually the same thing. Okay, this is what happens. Okay, now let's try to understand what is the meaning of self energy. Okay, So if you want to understand the meaning of self-energy, you just need to come back and look at this equation, right? So G inverse times G will be this quantity. This is the definition of G inverse, right? So G inverse looks like this, right? It is d by d tau Ck times some potential. What is the meaning of G? The meaning of G is the amplitude for propagation. I put a particle and I pull the particle out later, right? That's what this object is. There was a definition of t tau times that. So that's the amplitude of propagation, right? So what this says is that the differential equation of motion of that amplitude of propagation has the usual free particle propagation, which is this, and an additional time dependent potential which the medium provides you, right? And that is this thing called self-energy. So I have not calculated anything, I'm just stating it. This is just a statement. So the game now is to actually calculate this quantity, right? So you will find that when Antoine gives his talk on DMFT and so on, this thing will play a central role. It will be the most sort of, when you want to look for convergence of your DMFT solution and all, you'll make sure that this object in one iteration is not very different from the, or is within some tolerance in the next iteration and so on. So you'll see that it's a very important quantity. I will also illustrate that it will determine the self energy and so on. Okay, now our friend, you mentioned that this may not be diagonal, right? So the way I have written it, I have not assumed whether it is diagonal or non-diagonal. I have allowed it to be not diagonal, right? So what does it say? If I add a particle with momentum, sigma prime, right? It can get there is an amplitude that it may become k sigma, which means it can flip its spin as well as change its momentum. But if I have a system which doesn't break any symmetries, so for example, I have like a Fermi liquid kind of state, no symmetries are broken, right? Then what happens? This fellow will become diagonal in these indices as well, just like this guy. So the statement is that this guy, its structure is determined by the symmetry of the state. The free particle state that we wrote down, the free filled Fermi sea and the particle hole excitations of that at finite temperature, they are completely symmetry preserving. They don't break any symmetries, right? So if my state is of that nature, if I find the final answer that I'm finding a state which doesn't break any symmetry, then I can simplify this and say that this quantity then this quantity would become, k sigma k prime sigma prime of tau minus tau prime would then become equal to some sigma of k sigma. It depends only on one of the indices, tau minus tau prime, and then this picks up the conserving delta functions. So this says that momentum is conserved, and this says that spin is conserved. Okay, so that's what you will get. Okay. So far, much of what I've been doing is I've been asserting things. I'm not actually shown what this looks like for any system. I've not done any such thing. I'm simply making things plausible for you. Okay? Okay, any questions at this point? Yes?
So what kind of causality?
It will have the same causality as the, so okay, okay, that's a great question. So suppose I were to take this to the real time. So how would I do that? I would go to imaginary time first. I'll first go to imaginary time, and then I will do analytical continuation, go to omega plus, and Fourier transform it back to t minus t prime. Suppose I were to do that, you can show, it takes not a whole lot of work, but it takes a little bit of work to show that this has the same causality properties as G. Okay. 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 Any other questions?
Excuse me, sir.
Yeah.
I'm not sure, but suppose I have a Lagrangian which is like a function of a complex and a scalar field. And is this self-energy term is led to mass renormalization? Like I can add counter terms to make the ground state energy finite and one particle state like to make one particle state and ground energy same for interacting theory as well as free theory.
No, just one second. So you see, I don't need to add any counter terms and all as yet because I have not found any ultraviolet problems. I don't have, we are doing condensed matter. So all our scales are finite. Don't need to worry about any ultraviolet things. So we generically don't need to add any counter terms. That's point number one. Okay. But you are right. This, if, for example, if I have interactions, it can change the dispersion of my particle. So this term will change the dispersion of the particle. So Ck would have been the usual dispersion of the particle. This will add to that Ck, and it will change the effective mass of the particle. That's correct. But in our problems, we don't need to worry about renormalization issues generically. If you go to cold atoms and then want to do some other things, then you need to worry about renormalization.
Thank you, sir.
Yeah. Okay, other questions? Okay, if not, let me proceed, and I just want to show you that now I want to take this equation that I have written, which is a generic equation whether it's interacting or non-interacting, and I want to put this equation in frequency domain, right? So this is written in time domain. I want to write this in frequency domain. If I do that, what will I get? That's my question. Okay, everybody understood the question? So let's stick to the, I will ask the question in a simpler case. Let's stick to the case where it doesn't break any symmetries. So everything has nice delta function, so you don't need to worry about anything. Okay, so then you can show yourself that the result is something like this. G inverse of IKL, and I just need to put one label now. The reason is that I'm in this kind of state, which doesn't break any symmetries, multiplied by G K sigma of IKL equal to 1. Okay, you have to show this. You have to start from here, and you have to show that. Okay, this will be satisfied for every IKL. That's the result. Okay, all right. So what is G inverse of IKL? So what do I need to do? I need to take this guy and Fourier transform it. And you can show that that quantity is something very nice. It will be actually IKL minus CK minus sigma K sigma IKL. That is this quantity. This quantity is this. Okay? This is all mathematical exercise which you can very easily do. You just need to sit down with a pen and paper and just do it. Okay? All right. So what have I found? I have found that G K sigma of IKL is equal to 1 by IKL minus CK minus sigma K sigma of IKL. This is what I found. Okay. So now I ask you, if I give you this quantity, how will I calculate the spectral function? Spectral function is observable. You can shine light, look at electrons coming out, and you can measure the spectral function. If this is the formula, what is the spectral function? Sorry? No, there are two things to do here. Yeah, the non-experts. So first thing to do is to analytically continue this. First thing to do is you remember I'd drawn that picture here. I'll draw that here again. So what do I have after I've done this calculation? Let's say somebody found a way to get you this. So what do I have? I have these set of guys here at the fermionic Matsubara frequencies. This is a fermionic object. That is, the operators that go into this are fermionic. So I have this object at fermionic Matsubara frequencies. I first need to get it onto the real axis, right? So I get this onto the real axis. How do I do that? Let's not worry about it. Let's say that we can do it. And how will I do that here? Here it's very simple. So what I'll do, I'll take something like this, and wherever I see IKL, I'll write omega plus. Analytical continuation by chalk. Okay, so why is this generically not possible? Because we may not have an analytical expression for this. What we will end up having after you have done some quantum Monte Carlo or something is that you will have a set of numbers at each Matsubara frequency. So you don't know what is the functional form of this. You don't know. You just have a set of numbers. So analytical continuation, the game is you're sort of guessing what that function is. Okay? And you're guessing that numerically. Okay? And that turns out to be what is in mathematics called as an ill-posed problem, in the sense that small changes in the initial data, small changes in the values of sigma of IKL, for example, will produce huge changes in the value of A of omega or any such thing that you calculate on the real axis. Okay? So that somebody else will talk about, I hope, and we'll leave it there. Okay, so I get this. And what is this quantity? Here I've used curly G, and in the old notation I had used this capital K, and this is just this quantity. Okay, everybody's okay with this? So from here, what is the spectral function? Okay, it's very easy to write down the spectral function now. Okay, so the spectral function is just this quantity. Okay, so I have just used the fact that sigma can be written as a real part and imaginary part, and I have taken the imaginary part of this. Okay, now you will see immediately that this puts a very strong constraint on your calculation. Suppose you do some calculations, you do quantum Monte Carlo, you do whatever, you may do some diagrammatic perturbation theory, you may do whatever you want, some way to get this sigma, right? Because you want to calculate the spectral function. So you want to calculate the sigma. So you do that calculation. There is one immediate check you can see you should do to check whether you have done the calculation correctly. And what is that? What is that? Sorry? Excellent. So it should integrate, this result should integrate out to 1. There is something earlier you can check. Right, right. So this should be positive. So what that means is that the imaginary part of the self energy on the real axis coming from the top must always be negative, must always be non-positive. That's the precise statement. It's allowed to be 0, right? It should be non-positive, right? So it should, two things should be satisfied. D omega, ak sigma of omega should be 1, and this quantity should be greater than or equal to 0 everywhere. So that puts some constraints on that. So this will be an immediate check of any calculation you do, whether you're getting self energy to be, the imaginary part of the self energy to be negative on the real axis when you come from the top, omega plus, and you should integrate out to 1, right? Okay. Okay, any questions? Yes.
So is that analytical continuation with chalk, is that valid if I don't Fourier transform and just...
I didn't understand, valid?
If I replace tau by IT, is that a good analytical continuation from imaginary time to the real time?
It need not necessarily be.
So what's the reason that we are able to do it on the Fourier transform but not?
Because you see, nobody said anything about this function being, this being generalized. All analytical continuation is done in the frequency space. So that does not necessarily imply analytical continuation in the time.
Okay.
right? Because, yeah, all the action is taking place in the frequency domain. Yeah. Question?
So why is it not done on the time?
Why is it not done on the time? Because you see, we are doing, so this is like a linear response function. So for each frequency there is some characteristic response. So so it's like a linear response object, right? So each frequency is a property.
No, I'm saying the analytic continuation. Why can't we do it in time?
Why can't you do it in time? Okay, so there are several things. So you see, time in the real time actually goes from minus infinity to plus infinity. The imaginary time goes from 0 to beta.
Beta.
No, but even in frequencies are continuous and these are discrete.
That's fine.
So you can just replace now by I times t, and then you can say that it goes from.
Okay, so the question is what calculation you want to do and how you extract information out of it. So okay, if you want to push this thing of doing imaginary time continuation, etc., one can pursue that. But what I'm saying is, here is a way of doing a set of calculations, and it works.
And also,
Right. Yeah, super. Yeah, go ahead.
I was thinking if there's a simple explanation just in terms of Fourier transforms that so I guess if I understand the question correctly, suppose you have a function f of x and its Fourier transform is some f tilde of k, then your question is, suppose I write x equal to iy, then why is the Fourier transform not equal to f tilde of ik? Is that?
It may not even be defined.
Yeah, because at least if you're looking at it that way, then, meaning that you're doing the analytic continuation of the function as a function of x, but if you just naively look at the Fourier transform and do the analytic continuation, then it isn't even defined, because...
It may not even be defined, yeah.
Because, you have an integral which goes from minus infinity to infinity when you're integrating the harmonic function e to the ikx, and when you write x equal to iy, then it becomes integral of e to the ky from minus infinity to infinity, which isn't, it isn't even a convergent integral.
Yeah.
So,
but maybe we can pursue these things later, because let me tell you, we have a lot to cover. Huh? So I also want to add one more point. Okay, so I am actually not I'm actually asserting many things, right? I'm actually not deriving things and so on. So in many ways, what the philosophy I'm taking is what Mermin did when he teaches quantum mechanics, and he has written about it. It's called shut up and calculate. Yes. Okay. Yes.
So one more thing, we could have worked with the Green's function that was previously derived in terms of the theta functions, and just Fourier transform at that level and not do all these
No, but you see, no. See, the reason why we are doing all these things is that we can in one fell swoop get the time dependent response functions as well as solve the finite temperature problem.
No, I'm saying you went from the Green's function to its derivative and then Fourier transformed it just to make it a algebraic equation. So why not Fourier transform it and get it a algebraic equation?
No. So what? Okay. So I should have motivated it better. Okay. So the reason why I did all this stuff is that it turns out that the self energy is what we actually end up calculating, right? So we have ways of calculating the self energy. So from there we can. So there are systematic ways of approximating the self energy. So you can interpret the self energy as some quantum processes. So you can isolate what the important quantum processes are involved in your problem if you have a physical intuition, and then you can actually get very controlled approximations in at least rare cases for the self energy, and then you have some understanding of the system and so on. So it is very natural to do this in this way, and it may not be very apparent the way I have shown it. Okay. Yeah.
So I guess one good reason to look at the differential equation that the Green's function satisfies is that the self energy sort of very naturally enters that differential.
Exactly.
As minus d by theta plus c plus the self energy acting on g will give you.
Thank you. Yeah. Okay. All right. So now the question is, how do I calculate the self energy?
I have one question.
Yeah.
I was thinking if the self energy is some sort of correction for actual energy, then means how is it that it can be imaginary? Like I don't know. Means because if
No,
we
no, no, wait. See, I mean, let's stay on planet Earth. I mean, don't get into, we have very good understanding of what imaginary part of self-energy and all means. Okay, so the point is something like this. See, I can have some time-dependent potential, right? If I have a time-dependent potential, so if you go to the real axis, there will be a retarded time-dependent potential. That's all that is there to it. So a time-dependent potential generally will have, it may not be in phase with something. So when I have time dependence, I have something moving and I'm sort of driving it. So there may be a phase lag. So how do I capture that mathematically? So I put something complex. So that will say that something moving here may be lagging a little bit there and so on. That's why it's like that. So because I have particles moving, something moving here, it may take a little while for it to get here. So I have to put this time dependence, and the natural way to include all these things is use complex numbers.
actually this problem also, this lagging problem I didn't get because we never told instantaneous or action after some time or something like that kind of thing in our equation. We never said that these potentials are going to act after some time. If you look at the Hamiltonian.
So no. So we are not looking at the Hamiltonian of that is not the equation of motion of the full system. I have added a particle to the system and I'm asking what is the amplitude of evolution of that particle? So that particle is interacting with a whole bunch of other things. And when it is interacting with a whole bunch of other things, it is not seeing a static effective potential from the other things. Because the other things are not static. They are also moving around. That's why self-energy has that form, tau minus tau prime and so on. Okay. Yeah, this.
When we are extending our calculation for interacting system, so why exactly we are taking sigma to be a function of tau minus tau prime, not as a function of k as well?
It is a function of k.
It is a function of k. So in that case, when we do this inverse and take it ultimately to be a gk sigma, should sigma be a function of only Matsuura frequencies and not a k-dependent function?
Generically, it will be a function of also k, but Antoine will show you in infinite dimensions that k dependence will drop out.
So have we taken that k dependence at the first place when we are extending for?
Yes, we have taken that k dependence at that place, and all that I'm doing is that this will get a delta k prime, delta sigma sigma prime structure. The self-energy may depend on the momentum of the particle you are adding. But there will be no momentum changing self-energy process if my state is translationally invariant.
So that is only possible for infinite dimensional bath or infinite dimensional system?
No. In generic systems, this is true that if I have a state which doesn't break translational invariance, then added particle I can only pull out at the same momentum. That's one statement. Okay. Now, in infinite dimensions, what happens is the k dependence of that self-energy drops out. The self-energy becomes momentum independent.
So we have dropped it out somewhere here?
No, where have I dropped it out?
No, ultimately when it is a sigma
here.
ikl only. So that k as the suffix.
Okay, maybe this piece of the board, by the time it gets here, is actually sort of, that light is sort of dropping off or something. Because I have written k sigma here. Oh, here. Okay, fine. Okay. Yeah, actually there are refractive index fluctuations on the way. Is it what you want, Swagata? Is this what you want? Yeah, okay. So it's just a notational problem. I mean, it may be bad notation, but nothing, I haven't done any crime that you accuse me of. Yeah. Okay, other questions? Okay. So the path integral part is coming. I may be able to only do the path part. The integral may have to wait. Okay. Okay. All right. Now, I'm going to change gears. So I've shown you what we want to calculate. We want to calculate the self-energy business. Okay. So we want to find some techniques for doing these calculations. Okay. So to develop those techniques in the way that, for example, will be done in DMFT and in Quantum Monte Carlo, etc., I have to actually revise some background for you. Okay. And this background relates to Feynman's very insightful work. Okay. So the main idea of Feynman's path integral formulation is the idea that you can, instead of thinking in terms of states and Schrodinger evolution of states, you just think in terms of amplitudes of processes. Okay? So the idea of quantum amplitudes of processes taking place, they take on a fundamental role. So what is an amplitude? Let's just discuss that. So imagine that I had a particle here at some initial state, let's say Ri, at time t equal to 0, initial state, and let's say the particle, it evolves, and then you look at the final state at some time Tf. Okay, you just imagine this situation. So I have Hamiltonian for the system which I give you. H is the Hamiltonian. So I ask, suppose I create a particle at this position at time t equal to 0, what is the amplitude that it will be in the state Rf at time t equal to Tf? Okay. So we can write, I'll just formally write this down. This is Rf Tf, R initial 0. And we know from elementary quantum mechanics that we have all done that this quantity is just Rf e to the minus IHT f Ri. This is what it is. Okay? This is the amplitude of starting at state in Ri at time t equal to 0 and reaching the state Rf at time t equal to Tf. The probability that this would happen would be the mod square of this. Right? That will be the probability that this will happen. This is the amplitude that it will happen. Okay? So this way of writing it, the way I have written it here, is the Schrodinger way of writing it. That is, you have states and the states evolve in time, and you simply look at expectation values by sandwiching the evolution operator on appropriate states. Okay. So Feynman actually decided to do this in a slightly different way, and he sort of reformulated quantum mechanics, if you like. Okay. So what Feynman said is the following. Let's say that I have this thing. I start with these 2 points. This is these 2 states, if you like, Ri, and let me just write Ri here, and Rf. He said that this particle can go from here to here in the time interval Tf by some path. Which path? Any path. Right? So it could be some path like this. It will follow some path. The only conditions on that path is the position of the particle at time t equal to 0 is Ri, and the position of the particle at time t equal to Tf is Rf. That's it. Nothing else. Okay? All right. And he said that if I call this path as P, so P is equal to some function R of t such that R of t equal to 0 is equal to Ri, and R at t equal to Tf is equal to Rf. That's what this is. Okay. He said that this process, this quantum process of starting from here and ending there, has an amplitude. Okay. So let's call that amplitude as k of p. I have not told you what k of p is. It has an amplitude. Okay. This is statement number 1. So the path p has an amplitude. Okay, now we ask the question, what is the amplitude of starting at Ri at time t equal to 0 and reaching Rf at time t equal to Tf? What is the total amplitude for this process? So here is Feynman's point that in quantum mechanics, amplitudes add. So what do? You list out all possible paths that this fellow can take. Right? All possible paths. It's hard to even imagine all possible paths. Okay? It's a huge space of paths. Okay? So second is this quantity which we call as RFTF, Ri0, this quantity is equal to sum over, I don't even know exactly what I'm writing here, sum over the space of all, sum over all possible paths, okay, and this is KFP. So each path P is any nice function that will have this boundary conditions, namely at time t equal to 0 it's at Ri and at time t equal to this. Okay, so this is postulate number 1, this is postulate number 2. Now I need to close the loop. I mean, I need to specify everything. To specify that, I need to write out what is K of P. Right? Okay. So K of P, here I believe Feynman was inspired by some comments of Dirac. I may be wrong on the history, but that's what I have read. Okay. So K of P is equal to e to the IS classical of P. So this is the statement. So what is S classical? So I have this Hamiltonian of the system. I can write a Lagrangian for it. So and I can write a classical action for this. Integral 0 to Tf dt, whatever is the Lagrangian of the system. Okay. So now you see, if I put all these three things together, so the statements are, there is an amplitude, there is the sum total of amplitudes, and I'm giving a rule for calculating this amplitude, so you can even call this as 1A, right? Okay. So if I put these things together, then I get this very nice result, which says that this quantity KRFTF Ri0 is equal to integral, I will write something like this, d of RT like this, right, e to the IS classical functional of RT. So RT is just P, the path. And I have now formally written a measure in the space of functions. I don't know what I'm doing by this, but the space of functions, right? So okay, if you try to calculate any of these things, you'll get some nice answers called infinity and so on. Okay, so there are ways to calculate it, so we'll not get into all those details. Okay, so this is just conceptual statement and so on. Okay, any questions on this? Okay, if there are no questions, what I'm going to do is I'm going to show you that the partition function of our system can be written as a path integral. That's what I will show you. Okay, so how many of you have never seen Feynman path integral before? Never, ever. Yeah, you can raise. No, this. Okay. Not the, see, when I say how many of you have never seen Feynman path integral, it's not just see a printout of Feynman path integral. That's not what I'm asking, right? You must have worked it out a little bit, right? Okay. If not, I think you should. Sakurai has a very nice discussion of Feynman path integral, actually fairly accessible and reasonably short, in the sense that it is not. It's not like 20. It's not like 200-page book or something like that. So you can actually look at Sakurai. It's a good place. I would also recommend at some point of time you should read Feynman's original article. Right? It's called Space-Time Formulation of Quantum Mechanics. It's very nice. It's very nicely written. Okay. All right. So that's the story. Okay. Now the goal is to get a path integral formulation of the partition function. Okay, so why would you be, why would you think that this is possible? So the reason why you think this would be possible is the following. Let me write the partition function, right? So partition function is z. This is equal to trace e to the minus beta h. Right? So now what do you see? This quantity is sum over all states of your system, eigenstates, let's say, n e to the minus beta h n. This is simply the definition of trace, nothing more, right? But now you ask yourself, what is the meaning of this quantity in terms of an amplitude? What is the meaning of this quantity in terms of an amplitude? So this is the amplitude that I start with the state n, propagate for an imaginary time minus I beta, and reach the same state back. Right? So I start here and end here in imaginary time minus I beta. So this thing you can sort of think of, if I were to use that notation, this is kn minus I beta n 0. That's what that quantity is. Okay. Okay. So then we are very, already very, we see possibilities now, right? So what would we like to do? We would like to write this as something like this, right? So we want to write this as integral over all paths starting from at time t equal to 0 at state n, going to state n again in imaginary time, and write it as exponential of some classical action. Okay? Right? Everybody understands that? We want to write this in terms of exponential of some classical action. So we would like to write this as some path integral. I'll just write it as some path integral e to the some classical action. I'll put I here for now, but that I will go away in a while. Okay, so this is what we want to write. Now you see, if I had a single particle, this is fairly straightforward. What happens? I have a very nice definition of Lagrangian, for example. So Lagrangian would be something like t minus v. So I would write, for example, something like half r dot square. And if I have a quadratic potential, for example, I would just write something like some omega square, r square, or something. Some harmonic oscillator would have this as Lagrangian, right? Okay. Now, suppose I had two particles. Suppose I had two particles instead of one particle. Then in quantum mechanics, if they are indistinguishable particles, I have to specify whether they are bosons or fermions. So I have to specify their statistics, right? So now if I want to write some classical action, the bosonness and fermionness of the particle have to somehow enter into the classical action. So remember, statistics by itself is not quantum mechanics. Statistics is statistics. It just says that I have indistinguishable particles, and indistinguishable particles do various things, right? Quantum mechanics is something like uncertainty principle, that these two things are not simultaneously, diagonalizable and all that kind of stuff, right? So what I want to do is, I want to hold on only to statistics and write a classical version that respects classical actions, that respects the statistics, but don't worry about quantum mechanics. What will give me the quantum mechanics? This formulation will give me the quantum mechanics. The path integral formulation will give me the quantum mechanics. So what I want to do is, I want to derive a classical mechanics of indistinguishable particles with different statistics. That's what I have to do. Okay? So the statement of the problem is clear? Yeah. Okay. So let's do that. So let me see. So there's of course a lot of background, and I'm supposed to do path integral formulation of the Hubbard model in 2 minutes, right? It certainly cannot be done in this reference frame. I have to do some Lorentz boost to some other frame to do that. Okay. All right. So let me motivate this, and maybe I will continue tomorrow, and maybe we can have a little bit extra time. Okay. So how do I construct a classical mechanics of say bosons? So what is a natural playground to discuss bosons? So take this harmonic oscillator I wrote down here and write the quantum operator for that. So let's say look at a harmonic oscillator. Right? Okay, so what happens? I have p square over 2 plus omega square over 2 r square. So this is the typical things, typical Hamiltonian for a harmonic oscillator. Okay, so you know that this thing can be cast into some form that looks like this, right? Omega plus half a dagger a, right? These are the creation and annihilation operators or ladder operators of the harmonic oscillator. Okay. Now I ask you the following question. If I give you the harmonic oscillator, can you tell me what are the most classical states of the oscillator? Sorry? Coherent state. Wow, fantastic. Okay, that's a very nice answer. So how many of you do not know ever what coherent states are? Anyone without knowledge of what coherent states are? Okay, so you have time till tomorrow to pick that up. Okay, all right. So the so-called coherent states are the most classical states of the system. So what do you mean by most classical states of the system? So we know, suppose I give you a state psi. In this state, I can calculate what is delta p, and I can calculate what is delta x. And then I can take the product of these things. So delta p, delta x, by uncertainty principle has to be greater than or equal to h bar. In these most classical states, it will be equal to h bar. It is the best you can do. Right? That is the. So can you give me an example of a coherent state? Sorry? Ground state of the harmonic oscillator. Thank you. That's an example of a coherent state. Okay. So generically, the coherent state is an eigenstate of the annihilation operator. This is the definition of the coherent state. It's the right eigenstate of the annihilation operator. Okay? And what you can show is that you give me any complex number, there is a state like this. Right? Okay? And these are the most classical states of the harmonic oscillator. Okay. So now the question is, I'm not interested in bosons. This harmonic oscillator gives me bosonic operators. I'm interested in fermions. So my question, which I will start discussing tomorrow, is suppose I have a fermionic oscillator. A fermionic oscillator is like an orbital. You have, you take a Warnier orbital of some site, just take that orbital and throw away all the other atoms, let's say, right? And I have just that state. So how will I write the Hamiltonian? So the state has some energy, let me call it E naught, let's say. I would just write it as some C dagger C. That's it. That's the Hamiltonian. Nothing else. There's just this orbital. I can put a particle there, or I will not put the particle there. So the Hilbert space of the system is no particle, vacuum, or one particle. That's it. And this is Hamiltonian. Now what I want to do is, I want to develop a classical mechanics for this to describe this system. So that's what I want to do. And what will I start by doing? I have already seen that, if I have this kind of oscillator which looks like this for bosons, I will look, the most classical states are the coherent states. So the natural thing to do would be to look for the coherent states of this guy, right? So imagine that I had a coherent state, C phi, let's say, is equal to phi phi. So this will immediately give rise to a problem. And what is that problem? If I hit this one more time, C square phi, this is equal to phi, let me say it's a complex number, C phi, right? But that is just equal to phi square phi. But you see C square is 0, so that means phi square has to be 0. That means there is nothing like this. So you end up with some problems. So we have to now find a way to circumvent this problem. Okay? And that's what I will do tomorrow. Okay, we'll try to beat this problem. Okay, and we have to invent some new numbers and so on. Fortunately, we don't have to. Somebody else has done it already. Yeah. Okay. All right. Somebody did it. I think Grassmann was in 1800s, late 1800s, maybe early 1900s, something like that. Yeah. Yeah. It was done long before physicists got interested in it. Okay. All right. So let me stop here, and what I will do is I will develop a classical mechanics for fermions tomorrow.